All right, so welcome everyone. And in today's class, as you can see, we'll be looking at what we call the kinetic theory of matter. So we already discussed the gas laws, the ideal gas equation, the combined gas equation. We already looked at that in our previous class, and I just want to make this class as an addition to that one because I want to conclude on what we call the kinetic theory of matter. So initially today I was supposed to talk about those things again, but not in much detail. So I'll just peruse through them to remind each other about what we discussed in our previous class, and we're going to add on what will be our main focus today, of which in today's class, I want mostly to talk about the kinetic theory of matter itself, um, and also reiterate the relationships between temperature and average kinetic energy of molecules, and also show us how to calculate the root mean square speed of gas molecules, of which by so doing, we can also look at some of the assumptions that are applied on the ideal gases or on ideal gases, of which this is something that we basically already looked at last time. So without wasting much time, let's talk about the kinetic theory of matter today. So what is this guy known as the kinetic theory of matter? So we can just relate this to the fundamental concept. Let's say the fundamental concept. The fundamental concept that basically explains the physical properties of matter. I'll just say explaining physical properties of matter. Physical properties, uh, properties, properties of matter. And these physical properties that we're talking about when we are talking about the kinetic theory of matter, we're basically relating it to physical properties such as the motion and its constituent particles. So this whole idea is built around the principle that matter is actually composed of tiny particles. We already talked about this, such as atoms, molecules, and ions. And we also mentioned to say these particles are actually found in what we call constant random motion. So the more energy these particles will actually be having, the more faster they are going to move. And that, guys, is basically the whole concept that is surrounding this guy that we're calling the kinetic theory of matter. It's explaining to us the fundamental concept that is basically explaining the physical properties of matter, uh, mostly concentrating on its motion and the constituent particles. So we already discussed some of these things in our previous class, and even when talking about the ideal gas or ideal gases, we said there are key assumptions that we basically apply to ideal gases. And these assumptions that we apply are mostly just to simplify the behavior of gases. And we use this model that we call ideal gas to simplify that particular behavior of gases. And this model of ideal gases is based on several assumptions. I explained these assumptions last time before I even showed you how to derive the formula for the ideal gas equation itself. And just for a quick recap, what assumptions or what key assumptions did we talk about? We said or mentioned assumptions such as constant random motion. We mentioned to say gas particles are always moving randomly. So we mentioned to say we give an assumption to say the gas molecules that you're talking about are actually in constant random motion, which will be basically moving in a straight line until they reach at a point where they collide with something, or they collide with the walls of the container, or they collide with each other. The other assumptions you said that's negligible volume. Negligible. We talked about negligible volume, whereby we said if you want to talk about maybe let's say the volume of an individual gas particle, this or the volume of a single gas molecule or an individual gas molecule is actually considered insignificant compared to the total volume of the container that those guys occupy. So we say gases or gas molecules actually have negligible volume when you are comparing them singly to the volume of the container that they're occupying. We also talked about no intermolecular forces, meaning ideal gases do not attract or repel each other, which means there are no intermolecular forces that exist. So with no intermolecular forces, I'll say more forces. Another assumption that we talked about was that there is elastic collision, which means all particles between or all the kinds of collisions that that you can talk about between particles in a gas or between particles of a particular gas and with the container walls are perfectly elastic, which means there is no loss in kinetic energy. Kinetic energy is actually conserved. So we can just simply say there is elastic collision. Just trying to remind each other of these things, but we already looked at them in the previous tutorial when we were talking about the gas laws. And also we talked about temperature and kinetic energy, meaning the average kinetic energy of gas particles is directly proportional to the absolute temperature. Average kinetic energy, so I'll say Ke average, is directly proportional to what? To the absolute temperature. To the absolute temperature of that particular gas, meaning that if you cool a gas down to absolute zero, which you said absolute zero is basically a moment where there is no thermal energy in a substance. You have reached 0 Kelvin. When you cool down a gas to absolute zero Kelvin, all the molecular motion would theoretically stop because there is zero kinetic energy in that particular gas. So the kinetic energy or the average kinetic energy of a particular gas will actually be directly proportional to the absolute temperature, which means as you are increasing the absolute temperature, the average kinetic energy of this particular gas is also increasing. As you are decreasing the average kinetic energy, even the temperature, the absolute temperature of this particular gas is actually going to be decreasing. So those are some of the the assumptions that we talked about when we talked about this principle of an ideal gas, which directly leads us to discuss what we call the ideal gas law. And we discussed what an ideal gas law is, and we said if you want to describe an ideal gas in your own words, you can simply say it is a theoretical gas whose molecule have no intermolecular forces and undergo perfect elastic collision. So if you're describing an absolute or an ideal gas using what we call the ideal gas law, theoretically, you're supposed to include these assumptions that we've talked about here. So that means if I'm talking about the ideal gas law, I'm going to describe an ideal gas as a gas whose intermolecular or who has no intermolecular forces and it undergoes perfectly elastic collision. So mostly we can just say no gas is truly ideal, but this law or this model works well with gases that are under standard conditions. So under the ideal gas law, you can write this point to say no gas is perfectly ideal. It's perfectly ideal. But this model that we talked about, all the assumptions, how to describe an ideal gas law, is actually going to work well on gases that are undergoing standard conditions. And for those who remember, we talked about the ideal gas equation, and I'm going to not waste a lot of time. I'm just going to get exactly the ideal gas equation that you discussed last time and bring it here again because it is going to be the foundation of what we want to discuss today. So we discussed the ideal gas equation, which actually describes the behavior of ideal gases under standard conditions. And this ideal gas equation is described by the relationship between the pressure of that particular gas, the volume of that particular gas, and the temperature of that particular gas. So the ideal gas equation is primarily expressed in two different ways. Yes, it is primarily expressed in two different ways, of which one of the ways is in terms of the number of molecules, whilst the second way is actually expressed in terms of the number of moles. So you can express it in terms of number of molecules. I'll say number of molecules. Number of molecules that I can just say or represent with a capital N, but also the number of moles, which is represented by a small letter N like this. So in terms of the number of molecules, the ideal gas equation is equal to this guy. PV, I'm just going to write it because we already discussed this. PV is equal to N K with the subscript B there, capital T. So this is it in terms of the number of molecules, N. This is in terms of the number of molecules, N. Whilst if we are expressing our ideal gas equation in terms of the number of moles, we say PV, which is pressure multiplied by volume, is equal to N RT, where T is temperature in Kelvin. So these are the two ways in which you can express our ideal gas equation. So on the first formula here, or on the first equation, P is for pressure, as usual. V is for volume. This capital N there is representing the total number of molecules. So N is the total number of molecules. So I'll just put here total. Whilst KB, this guy, is what we call the Boltzmann's constant. Boltzmann's constant with a magnitude of 1.38 times 10 to the power minus 23 joules per Kelvin. So this is the Boltzmann constant, which is used when you're trying to, or when you give out your ideal gas equation in terms of the number of molecules. So Kb is representing the Boltzmann constant, which is having that magnitude there, and T is temperature in Kelvin. Remember the temperature here, or absolute temperature, we can specify to say absolute temperature in Kelvin. Plus, if you talk about this other formula, we are talking about P being equal to volume, P being equal to pressure rather, V for volume, small letter N for the number of moles. Number of moles, whilst R is the universal gas constant. We already talked about this. R is the universal gas constant. And there are actually two values of the universal gas constant that you will be given in different scenarios. And mostly it's going to depend with the units of measurements that you are going to use, because they are actually the two of them with two different numbers and two different units. So it depends with the units that you are given. That's the one that you're going that, or that's the universal gas constant that you're going to use at that particular instant. If you are given moles or mole per Kelvin, you can use 8.314. I mean, if you're using joules per mole per Kelvin, you can use 8.314. Whilst if you're using the other one, you can also use, or if you're using calories, the one that is related, or you're dealing with something related to calories, you can also use the other one with a different magnitude, of course. So these are the two equations that we call the ideal gas equation. But what we must keep in mind is that for these formulas to work correctly, we must always be consistent with our units, which means our temperature is always supposed to be in Kelvin, and the standard temperature at standard temperature and pressure should always be also considered as 273 Kelvin, which is basically 0 degrees Celsius, and the standard pressure is 1300 pascals at standard temperature and pressure. 273 Kelvin, 1300, or I can say 1300 pascals, which is basically 101300 pascals. So how do we find the number of moles in these cases? Calculating the number of moles or finding the number of moles using different relationships. So we already know from chemistry to say if you want to calculate your number of moles, you can basically say the number of moles is equal to M over capital M. Or if you are relating this to the number of molecules, which means those two equations, this one will be the one where you are expressing your equation using the number of moles, whilst this one will be in terms of the number of molecules. We're going to say N over N A. And what do we mean? We have capital M here as a denominator, whilst we have small letter M as a numerator. The small letter m is the mass of the substance, and the capital M is the molar mass of that particular substance in this first formula that we have here. Whilst if you're looking at this other one, the small letter or the N that you have as a numerator is the number of molecules, whilst this guy, the denominator, is what we call the Avogadro's number, the 6.02 times 10 to the power 23 molecules or per mole, molecules per mole. That's how you're going to calculate number of moles in different scenarios. So we'll look at examples mostly in our next class, but let's also remind ourselves on the combined gas equation. We said the combined gas equation is P1 V1 over T1 being equal to P2 V2 over T2. These are some of the things that we already discussed in our previous class, and for today, let's now look at the kinetic energy and the molecular speed. And molecular speed. Okay, so the first question I would love to ask is that we know to say gas molecules possess what we call kinetic energy, and we say the average kinetic energy of a gas is directly proportional to the absolute temperature of that particular gas. So how can we actually calculate the average kinetic energy? Because we already talked about how this links or how the kinetic theory is going to directly link temperature to the energy of gas molecules. So if we want to calculate the average kinetic energy of a single gas molecule, we are going to use this particular formula. We'll say Ke average of a gas molecule will be equal to 3 over 2 K with a substitute 3 T, like this. This is the formula that you are going to use to find the average kinetic energy of a single gas molecule. And this is actually a crucial result because temperature is directly, or the absolute temperature is actually a direct measure of the average kinetic energy of a molecule that you're going to talk about. And if this is the formula we are using to calculate the average kinetic energy of a single gas molecule, how about if we want to calculate the total kinetic energy of all gas molecules? How about if we want to calculate the total kinetic energy of all gas molecules? So we're going to say total Ke will be equal to 3 over 2 multiplied by what? Multiplied by N, which is the number of molecules, multiplied by Kb, which is the Boltzmann constant, multiplied by T, which is the absolute temperature. And this formula is the same as 3 over 2 multiplied by N, which is the number of moles of that particular gas, multiplied by R, which is the universal gas constant, multiplied by T, which similarly translates in the same way to 3 over 2 PV. pressure multiplied by volume. So this is how you calculate the total number of, or the total kinetic energy of a particular gas, or the total kinetic energy of gas molecules, of given gas molecules. This formula, if you check, it's directly coming to these two formulas that we had written here. The ideal gas equations, or the two forms of our ideal gas equation. Even when we want to calculate the total number of, or the total kinetic energy of this gas, we are going to use these, or we are going to relate it to these formulas that we've been given here. Because if you notice, this is equal to this, and this is similarly equal to that. So what did we do? We used this, that, and did that, and just got them directly and inserted them into this formula for calculating the kinetic energy of a single gas molecule, to come up with a formula on how to calculate the total kinetic energy of given gas molecules. And since we have talked about molecules in a gas moving at many different speeds, we discussed to say molecules in a gas actually move at different speeds. When you want to talk about the speed of those molecules, or you want to talk about the collective speed of molecules, of gas molecules, what do? We talk about their average speed. This average speed that you talk about when you're describing the speed of, or the collective speed of individual gas molecules, is what we call the root mean square speed. The root mean square speed is the speed that describes the average speed of gas molecules, or the average speed of gas molecules. Since we know to say gas molecules, or different individual gas molecules, will actually be moving at different speeds depending on specific characteristics that are being applied to that particular gas molecule. But if you want to describe the speed of gas, we often talk about their average speed. And this specific type of speed is what we call root mean square speed. And this guy can also be calculated directly from the temperature. And for us to come up with this formula, or for a single molecule, come up with a formula for calculating the root mean square speed, we are going to derive our formula from the kinetic energy formula. We know to say kinetic energy is equal to half mv squared, like this. And we said when we are describing gases, or want to find the average kinetic energy of a single gas molecule, we say this is equal to what? This is equal to 3 over 2 kb multiplied by 2. So the Boltzmann constant multiplied by 2. So this is going to give us what? Our V RMS, root mean square speed, or root mean square velocity, I don't know, whatever I can call it, will be equal to what? It will be equal to 3 kb T over m, where uh, m is the mass of the molecule in kilograms. This guy that is here, m is actually the mass of our molecule in kilograms. So for this is for a given mass of a gas. What about when you've been given a mole of a gas? How is this formula actually going to look like? So when you're using moles, when given moles of a gas, this formula is also going to be related to moles. How is that going to happen? We're going to say our root mean square velocity will be equal to the square root of 3 RT over m, where m is the molar mass of the gas in kg per mole. Molar mass of the gas in kg per mole. So this is how you can calculate your root mean square speed of a gas, provided you've been given mass of a particular gas, or either moles of a particular gas. You're going to use these two different formulas, but remember, the differences in these formulas are due to the fact that when we are talking about ideal gases, you can talk about them with respect to sometimes moles or sometimes number of molecules, and that distinct or those two distinct scenarios are the ones which have led to all the differences in formulas that we've actually come across, even the ones that we are going to use to calculate the total kinetic energy of gas molecules. These ones that are here, we used or we derived them due to the two forms of formulas that we can actually end up with when we're talking about the ideal gas equation. So that, ladies and gentlemen, is what I wanted to talk about under the kinetic theory of gases. We'll look at examples in our next class, and make sure you subscribe to my channel, share this video, and register with our tuition center. Thank you very much, and stay blessed.